Do, do. 11/10. All right. Hello, guys. Welcome to the last recitation. So we're gonna talking about the particle filter and maybe one of the HMM example if we have time. So all right. So let's see. What do we do? Particle filter. Particle filter. Okay. So we can go to the recitation pad first. Let me paste it in the chat. Go there. And I'm gonna share my screen. Share screen. Share screen. One. Share. Give me a new pad. Okay. So particle filtering should be really straightforward. What's my note? Okay, it's here. Dismiss. Go. To page 19. All right, page 18 is the one. So we were trying to localize our robot given the sensor reading. All right. So what today is 24th. Particle filter. So the algorithm should be really straightforward. So the first step, you're reading the map. Parse the map. All right. So if you look at the shared screen, I can go to Can everybody see my screen still? Does it work? Wait, so where is? I have to bring this to desktop 1. Wait, what happens? Oh yeah, here. Okay. Oh yeah. So this is the input of what is the file name? Altogether input. I think it is the test standalone, which you give the map and the sensor reading in one file. So the first thing you have to do is parse the map, because in the simulation the sensor reading gonna given, so this part gonna give separately, right? So you pass the standard in all the way to the map. So that is the step 0. So okay, let's shift it back to here. And then what you do is you parse the sensor reading. parse the, I think the action command. So let's say you want to go up, right? Go east. So pass the command until the end. So if you read the end, you terminate the program. Otherwise, you're gonna keep looping. So after you pass the map, you're gonna read one of the command, and then the second command until you read a line called end, then you can terminate. Otherwise, you keep doing this update, particle filter update, right? So after you read one of the command line, what you do is you move all your particles. So for each particle, you apply the movement model. Right? So update your particles, then you adjust your weight. So close to 19. And then you print it out, you spit it out. So after you adjust the weight, you can do resample to generate a new bunch of samples. Then go back to step 1 to read. Once you have the new bunch of samples, then you do the next action and then observe the next observations. Keep doing this, and then update your filter, update your particles. In the end, the particles gonna be around the ground truth, right? So any questions regarding that process, the particle filtering update? So later on, I gonna show you how it works with the simulator, right? Okay, so yeah. So yeah, basically what you do is, first of all, and you do the test on the test standalone to debug your program. And then you're gonna see all the actions you give, all the new particles you spit out each step. So just make sure the format is correct. And then since you cannot see the performance of the algorithm, so we provide this MCL Monte Carlo localization tester .py. And then you run that with your executable. So here I run 1000 particles, and then give only the map file. So the big map file or the small map file. So only the map file. Then the actions and then the observations gonna be given by the harness, the tester. All right, let's run this. So if you run this, you will see UI, and then you have the ground truth here. Yeah, like the gray circle here, and then you're starting to sample your particles. You put 1000. So first step is parse the command. Right now you can hit the up, down, left, right key. So you go up, and then you parse this this action for go up. I think it's yeah, go north. maybe go up. And then you sample, right? You sample 1,000 samples, uniformly distributed in the map. And then you move each particles by doing go up, and then see the observations, what you have. Some of particles, if you go up, it's gonna hit the obstacles, so it's gonna die. So some of go up, you have the same observations, so it's gonna be live. And then you reduce the samples by according to the weight. So, and then you can receive the next action, like go up again. Like you see that my particles dramatically shrink around the ground truth. And then if you keep doing actions and then get observations, you can see some behavior like this. If you see some behavior like this, which means your algorithm probably is correct. So that all the particles should get around the ground truth, and then there's some portion of random samples still around the map. Right, that's how you use the tester, and then that's what you should expect to see in the end of your particle filtering algorithm. If you keep moving and then your particles not going around your ground truth, then definitely something wrong. Right? It shouldn't take too long to implement this, and then so you guys can have more time on the project. All right, if you have more questions regarding the filter algorithm, post it on PS and we can help. All right, any questions so far?
With the simulator, is it like if you hit north or whatever, is there still like a chance that it doesn't print out north, like with the 0.7 chance, or is that something else?
If you hit the up, yes, there's still some. I think regarding to the handout, there is some probabilities it wouldn't move up. Yeah, I believe so. So given an action, the robot correctly execute action with probability 0.7. All right. So it's only 0.7 chance it's execute this action. The robot goes 9 degrees off the intended direction with 0.1. So if you want to go up, and then you have 0.7 chance end up in the up position, but 0.1 chance in the left, and then 0.1 chance in the right, and then 0.1 chance you don't move, stay around.
So is that like implemented in this simulation?
So it's just no. It should be the robot correctly execute action with probability. Stay simply integer.
I tried in simulation, and my robot goes like in 90-degree direction sometimes. So I think it is implemented in this
yes.
simulation.
Yes, it's in the simulations. So yeah, if you look at this gray stuff, if I keep hitting up, yeah, you see sometimes it goes left. So yeah, it's implemented in the simulator. So if I keep goes right, it has some chance to end up in not in right. Left. Yeah. Okay.
All right.
So
Thanks.
that's stochastic word. Yeah. Question. Stochastic word. More fun, more realistic. Okay. So if no more questions, we can move on to do HMM example that we really don't have time to do in the class. Sounds good. So okay, this HMM, very powerful algorithm. It must running in your router, running in your car, running in all the stuffs nowadays. Let's see. Okay. HMM. So the power of HMM is you can only have the observations, and you only have the observations, and then you want to estimate the real state. Like if your girlfriend always behave randomly, and then you don't know if she really happy or not, by observation what she said, you can guess what's the real moon she has, kind of thing. And then yeah, very, very powerful. So if you only have, for example, if you want to fix the satellite up there, and then you don't have the real state, you don't know what's happening right there, but you only have some sensor data, and then you want to guess what's going wrong. So it's using a lot in NASA, I guess. And yeah, so let's try to do this. So the basic idea is you get some history data, right? You have a state sequence, state 1, state 2, state 3, state 4, state, and then for each state you have the observations. Like in state 1 you have observation 1, in state 2 you have observation 2, in state 3, all the way. So you have this history data. So this is the history. And then given a new observation sequence, like O(n) plus 1 all the way to O(n) plus n, what's the most possible sequence of real state behind this? So what is the state n plus 1 all the way? We want to guess. We want to make the best guess of what's the best sequence of this. Right, very, very powerful. And okay, so one example Wheeler want me to, so okay, oh my god, it's a maximum 20 pages for the recitation pad. I cannot hit the next button. Oh, I don't encounter this. So what do we do? Anyway, all right, I gotta erase everything here. All right, everybody got this? So we have the recordings, so we still good, I guess. I'm gonna clear the frame. All right, so the example we're gonna do is think of you're in a house, and there's no windows, right? This is you. There's no windows, and then you cannot go outside, but and the weather can be either raining or not raining. Rain or not rain. The weather, and then you can only observe people going to the house. Some people going to the house every day, and then with or without umbrella. People have an umbrella. And then someday people going in without umbrella. Someday people going in with the umbrella. The observation you can see is umbrella or not umbrella. All right. The state is rain or not rain. So basically the mark of state representation is either rain or not rain. This is your state. Then they can transition into each other. All right, and then you have some observations of umbrella. Then you can also observe not umbrella. Right. All right, let's I think there is we shouldn't do too much on this. Okay, and not umbrella. And then in the rainy day, you can observe the people. You have only one guy going to your house. So let's say it's John. So John have the umbrella in the rainy day, not have the umbrella in the rainy day. If it's a not rainy day, you can observe this, some probabilities here. All right, this is our Bayesian net, basically the causal graph. the probability graph we can have. All right. And then given some history data, we know the probability of raining of the transitions. Let's see how we, all right, so do I want to clear this? Yep, let me clear it. Already. So all right, so I will just write down there. So the history data we can have is the transition of raining to not raining. So if it's raining is true, and then the probability of the next day, so on day t minus 1, right? The probability of raining on the next day t is 0.1. No, sorry. Is 0.1. And then the probability of the next day is not raining. T. Not raining is 0.9. They have to sum up to 1, right? If the day is not raining, and then the next day it's raining is 0.2. Then the next day it's still not raining. It's 0.8. All right, you got the idea? So this is all from the history data. We know the transitions of the day. If the previous day is raining, we kind of have a probability of know the next day it's raining or not. And then if the previous day is not raining, and then we also the probability to tell us if it's gonna raining or not, the transition probabilities. All right, and then we also have this observation model we built based on the history data. So let's clear this. So the observation data. So if it's raining, raining is true. So the probability of you observe an umbrella is 0.9. So rainy day, this guy have 0.9 chance to take the umbrella. The probability of not umbrella is 0.1. And then if it's a not rainy day, and then the guy have a 0.05 chance to take the umbrella. You have 0.05 chance to observe the umbrella. And then you have 0.95 chance to not observe the umbrella. All right, that's our observation model. So, okay, yeah, why I do this? I actually have prepared the example, all right? So, okay, still I can scale up this. Yeah, that's what we have. All right, so from the history data, we counting the days raining, and then we counting the days not raining, and then to observe the chance that how they transit. And then we also counting the days that we know it's raining, and then we observe the guy have the umbrella or not. Once we have the history, and then given a new sequence of observations, say I'm blocked inside a house, but I have the history data. And then I observe the guy have the umbrella, and on first day, it takes the umbrella. On the second day, he didn't take the umbrella. The third day, he do bring the umbrella. So I want to guess what's the best chance of if the first day is raining or not, the second day is raining or not, the third day is raining or not. All right, you only have the observation, but you want to guess the real state beyond this. And then we're using the algorithm called the Btob Decoding, which is a very powerful dynamic programming approach. Let's see how we do this, right? So, okay, this is So let's say we know that the day before it's not raining, and then we receive the 3 sequential observations: umbrella, not umbrella, umbrella. Okay, we get this sequential, and then we want to predict the most possible state sequence. So the day before it's not raining, and so the value, the probability value for not raining is 1, and then for raining is 0, right? And then yeah, I don't. Class. It's 730. 730. Btob decoding. Yeah, we're gonna doing update by timing together, multiply together the transition probabilities and the sensor model, the sensor data. The sensor model times the transition model times the value we have is what are we gonna do for each state all the way from the beginning. All right, so for day one, right? So the probability, if the previous, we can have two transitions. We either transit from not raining, the previous day is not raining, and then transition from the previous day is raining. So if the previous day is raining, the previous value is 0. And then the transition probability, transition from a rainy day to a rainy day, if the day is raining and then the next day is also raining, the probability is 0.1, right? So this is from the transition model. And then also the sensor model. So on day 1, we observe the guy bring an umbrella. So and then we are computing the day for raining. So if it's raining and then the guy bring the umbrella, the observation model is 0.9. So we have 0.9 chance to see the guy have the umbrella, right? Then this gonna give us 0. And then we can also transit from the not rainy day. So if the previous day is not raining, the value is 1. And then the transition probability from not raining to raining, from not raining to raining is 0.2, right? 0.2. And the probability of we are in the day that is raining, but we also observe the umbrella is 0.9. So the sensor model is 0.9. So we got 0.18, I guess, 0.18. And then I guess this is the value we want to keep for this state. All right, so by looking at the vector, we have the scores. This is the score we just compute. And then we keep the maximum score if the score is greater than the one we have. So we can initially maximize them all to 0. So this is the score we have. So yeah, maybe I can share this to you so you don't have to. So yeah, I just share this this sheet with you guys so that you don't have to copy anything. All right, so then we compute this the day 1, the value of not raining. All right, it's all dynamic programming from the previous state transition. So if we transit from not rainy day, the previous value is 0. And the transition probability from not raining to raining to not raining, if the previous day is raining and today is not raining, so previous day is 0.9. Transition probability 0.9. And the observation model, if it's a day that we observed some guy, this guy have the umbrella, this is the first day, this guy have the umbrella, and he's not, and then we are in a not rainy day, but we observed umbrella. The observation model gives us 0.05. 0.05. This will also give us 0, I guess, because the previous value. Right, and then we compute this and transition from not raining to not raining. So from not raining to not raining is 0.8, and then the previous value is 1. And then the transition model is 0.8. The observation model is still 0.5. And that gives us get 0.04. Right. 0.04. So this is the value that we're gonna keep along in the while loop. So we always keep the score in the while loop. All right, so these two values, the larger one is this one. We keep this value. Since you have the link, I guess I don't have to do it so large. Right, then we do the update for the second day. So you see that it's a linear process. So then because all the dynamic message is summarized in this value, right? We don't have to look at all the combinations of all the sequence. Here we only look at this value. So all right, so for day 2, if we transit from the previous day of rainy day, the previous value is 0.18, and then the transition probability of from raining to raining is 0.1, and the observation model, if it's a rainy day and then the guy does not have an umbrella, is 0.1. So the value is 0.0018. Right, and so if we transit from not rainy day, so the previous value is 0.04, and then the transition model, the previous day is not raining, today is raining, it's 0.2, and the observation model is still 0.1 because the day of the observation is not umbrella. So that would gives us yes 0.0008, right? So I think 0.018 wins. This guy wins. So the value for this state is this. And we also compute the value for not raining. If the state is not raining, and then we do it from our transit from previous state value. If a previous state is not is raining, and the transition probability, and then the transition probability from raining to not raining is 0.9. And the observation model, if it's a not rainy day, the guy have 0.95 chance that not take umbrella. So it matches very well with our observation model. So the value will give us 0.1539. Right, the last value we have to compute is from not raining transit to not raining. Transition model is not raining from to not raining is 0.8, and the observation model is also 0.9. This gives us 0.030. 0.04. Yes. Note. So these two guys, this guy is larger. We prefer. Oh, why am I using? Yeah, maybe I should use the green. Okay, it's larger. Everybody understand? Following along, okay? What are we doing here? If it's okay, can you hit a 1 in the chat so I know that everybody following along? Nice. Okay, so that's a pretty much handmade implementation of this algorithm. So I guess it's a little bit painful to do it by human, but let's finish it. So the same thing, right? So it's a linear process. So for these three, we can see that we can transit from the rainy day to rainy day, and then the transition probability is 0.1, and then the observation model we have an umbrella, and then we have an umbrella. It's raining, 0.9 chance to observe that. So this is and so then we can transit from the previous day, which is not raining, 39, and the transition model is 0.2. The observation model is 0.9. That would give us take this closer. Zero two 7702. This gives us this. Yep. All right. And then the previous day is raining. Today is not raining. The previous value is 1.8. The transition probability is 0.9. Observation is, since we don't have the umbrella, right? We have the umbrella, and then we have the umbrella, and then if it's not raining, the transition probability is 0.05. Very low probabilities to observe that. So, and then we can transit from not raining. So what's the number? This one gives us is 0.1539. Transition from the let's maybe I want to 0.8, 0.05. All right, yeah, finally 36156. Yeah, finally we compute the last day, and then we also find the larger value for these two. So this gives us these two. I think this one is larger, right? And then now we have to decide. Okay, let's see. Backtrack from S with the max value. So once we do the dynamic programming, we just look at the last step and then pick the best value. I think it's this value is larger than this. So we predict the last day should be a rainy day, right? And then we backtrack where this state comes from. This state actually comes from this state. So the day before the last day is not rainy day. And then this date is actually comes from here. So the first day is a rainy day. All right. So this is our the Viterbi algorithm tells us, given the observation of umbrella, not umbrella, umbrella, the best possible sequence underneath is raining, not raining, raining. Yeah, very match with. So if this is how you compute it, and if you have the history, the real data the day before, so you know that the day before it's not raining. If you don't, just assign this value to 0.5 and then this to 0.5 and then start this process. I think they give a very similar example in this YouTube videos. Feel free to go there and then check it out. It's a more complex but very similar examples on this, how this work. So only given the observations, how you guess the state. All right. Any questions? Any questions regarding the process, how we compute this? All right. Hopefully you got it. And many of my friends get their first job, either in Google or Facebook. Many of them is to implement HMM and to do the work, to guess what's the best customers behavior, or because you only have this data, so you don't have the real state match. So it's a very powerful tool and then very easy to implement, by looking at this. So this process is going to be very easy to implement, several lines of code, because Google and Facebook has a huge data. So by doing the data, doing the counting, you can have a very accurate transition model and then other observation models. And you can do a lot of stuff by giving this data. All right. So oh, cool. If no more questions, that's it. That's it for today. Well, that's for me. And then good luck on your projects, guys. Bye bye.